So today, two topics, two different topics for today. So we'll start off with gradient echo, because we did spin echo last time. So gradient echo, and then I'll talk about the first of the lectures that are directly relevant to the homework, which is how to sort of apply and reapply the Bloch equation. So we'll start off with the simplest possible thing, which is just a series of RF pulses, a uniformly spaced series of RF pulses. So gradient echo. So what did we do last time? So last time was spin echo, and spin echo was where you do an RF pulse, and if you didn't do any other RF pulses, you would just get an FID, sort of like just a signal that would come out of the sample for about 1/10 of a second and die away. But if you do another RF pulse, within half a second or a quarter of a second, something like that, what happens is that amount of time after the second RF pulse, you get an echo. And I always pitch spin echo, it's a morally upstanding echo. Because if you hadn't done that second pulse, then nothing would have happened. The signal would have just gone away. But you inject some energy with the second pulse, and then you expose this hidden magnetization by this sort of get the guys who are ahead behind, get the guys who are behind ahead mechanism. So gradient echo is kind of like a not as good of an echo. So basically the way gradient echo works is you turn a gradient on, and just in words, what's a gradient? Well, it changes the precession frequency. That's kind of like the same thing as the T2 prime part of T2 star. It's damaging the signal. It's getting it out of phase. So you turn a gradient on, get it out of phase, and then you put it on the other way and get it back into phase. So you can sort of see it's a little bit like spin echo in that you got this like get some guys ahead, and then whoever's ahead you get them behind again. But it doesn't actually give you something that you wouldn't have gotten if you had just done nothing. So if you just done nothing, you would get sort of the decay of the FID. If you do a gradient echo, what you'll do is you'll add extra damage and then fix that damage, but you'll just get back to where you would have gotten if you hadn't done anything. So we'll go over that. We'll go over that with some diagrams, and then when we're done with that, we'll go to the saturation recovery. But let's just go back quickly to review what the gradient is, just to make sure that we can distinguish the different kinds of gradients. So here's a happy person in the magnet, and so this person is having an X gradient turned on. And so what does the X gradient do? Well, at a particular point, or say a particular line across the person, if we look at each point along this line and look at what the B0 is with the gradient off, you would have like a really big B0. So here's the B0 vector. And if everything was perfect, it would be the same everywhere. So that's the B0 vector. And so when you turn the gradient on, what does it mean to turn the gradient on? It's basically another thing that adds to the Z component. And what I'm drawing here is the X gradient. So what it does is it subtracts off some Z component here, and then less and less until you get to the middle where it doesn't do anything. Then it adds on some Z component here. It just adds it on to the so that's the X gradient. Now, what does it mean to turn on a stronger X gradient? It just means, do something like this. So this guy is, stronger. So we're not going to draw the gradient as a gradient. We'll just draw the strength of the gradient. So there'll be a bunch of graphs that will have the strength of the gradient changing. What that means is just how steep you turn the gradient on. And you can turn the gradient on the other way. So this is the opposite sign gradient. So that's, that could be a negative, depends on what your conventions are, but if this one was a positive gradient, that one would be a negative gradient. So that's the meaning of a negative gradient. So in that case, you would be sort of adding some z component on over here and subtracting some z component from this side. So that's the x gradient. But you could have the same thing for the y gradient or the z gradient. So let's just quickly draw what the y gradient looks like. So now we've got to draw it from the side. So here's the person from the side. And so now what does the y gradient look like? The y gradient is going to, if here's your large B0, what the y gradient is going to do is add some additional z component as you move in the y direction. That's the meaning of the y gradient. So here we're moving in the y direction. That's y, whereas this direction was x. So we move in the y direction and we add some B0 on. And you could do the same thing for the z gradient. You change the z component when you move in the z direction. So there's three. Those are the three different gradients, and so that's what we're talking about. So why mess around with if gradients mess up the signal, why mess around with them? Well, if we want to make any kind of an image, we need a gradient. And so virtually all the data that you record in the MRI is recorded with a gradient on, and so that's the reason why we mess around with gradients at all, because otherwise they would just, they just kind of mess up the signal. They get it out of phase by causing the protons at all these different places to process at different rates. And what does that do? Well, that just, causes them to cancel each other out and reduces your signal. But every time we record any data, and if we're doing any kind of imaging, which will be, starting next week, we need a gradient on. So that's kind of the motivation for the gradient. So what does gradient echo look like? So gradient echo is we mess it up. It's kind of it's not as morally an upstanding of an echo as spin echo. So we'll have three parts here. So we've got RF transmit. So this is RF transmit. So put stuff in. This is, let's say, the gradient, the strength of the, say, x gradient. So that's what it means. It just means the strength. So it's just how steep it is. Strength of the x gradient. And then this is RF out. RF, record. So here's our pulse, some kind of RF pulse. Doesn't have to be 90, could be whatever. And so what will happen is when we do that, we would normally get some oscillations to come out of our recording. But now what we're going to do is we're going to turn the gradient on like this. And it's always sort of drawn as a trapezoid, and what's the reason for that? Well, if you suddenly turn the gradient on, super suddenly, what's going to happen? We know from some of the equations a couple lectures ago that if you suddenly change the magnetic field, that causes a current. And then vice versa, if you have a current, that will cause the magnetic field to change. So if you really suddenly turn the gradient on with your 1.5 million watt amplifier, it's going to cause all these all these currents to flow around in the metal of the magnet, and that can cause trouble. And so you can't turn it on infinitely fast. There's a little bit of a ramp to it, but that's why we always have those ramps. So now what will happen to our signal? Well, say our signal was starting up here, and let's say that if we hadn't done anything, this is what we would get. So what is that curve? So that curve is basically e to the minus t over t2 star. So that's has t2 star, so it's got these little local static offsets that are causing dephasing, and then it's got all the rapid jiggling from all the adjacent protons that's causing them to get out of phase. So that's the. Now remember, when we were doing spin echo, there was another shallower fall-off curve like this. It's supposed to be falling off. I didn't quite fall off properly. So that guy's falling off too. And what's that one? That one was the one that we could get back up to if we did spin echo. So that was e to the minus t over t2. But now we've got the gradient on, so that's a third thing. So there's T2-like things going on, rapid jiggling. There's some local magnetic field static differences in different parts of the sample. That's causing some additional fall off. And then plus we got the gradient on. And so what's going to happen is the oscillations that you'll see will fall off much more rapidly than they would otherwise. So the curve will be something, say, about like that. And so what is that curve? We'll call that curve, we'll call that one e to the minus t over t2 star star. So it's got it's got three things going on. So it's got the rapid jiggling, the static offsets, and then you've got the gradient on also. And so what will happen is that those oscillations will fall off much more rapidly than they would if we hadn't done anything. So we're actually sort of damaging our signal. But then what happens is at this point, we just turn the gradient on the opposite way. So if we turn the gradient on the opposite way for the same amount of time, and we'll talk about this more next week, but the gradient, if you turn a gradient on for a certain amount of time at a certain strength, you can get the same effect by, say, turning it on at twice the strength for half the time. So it's a combination of how long it was on plus how strong it was. And so what is another way of saying that? It's the area under the curve. It's like, how big was the gradient and how long was it on? So you have to sort of calculate the area. And so if you do this, if you make these guys the same, so if these areas are the same, then what should happen is, right at this point, we should get back up to where we would have been if we hadn't done anything. So what will happen is, at this point, these guys will start getting back into phase, and then they'll come up, and at this point they'll reach the e to the minus t over t2 star curve, which is what would have happened if we had left the gradient off completely. And so you'll get an echo. It looks just like a spin echo like that. So that's a gradient echo. So it's not a very morally upstanding echo. All you did was you did some damage, and then you undid the damage. And when you undid the damage, you just basically got back to where you would have been if you hadn't done any damage. And then notice that, let me move this one over slightly. You can see that the echo is falling off again because we typically leave the gradient on. So we would typically leave the gradient on for another chunk and continue to mess up the signal. So we'll mess up the signal afterwards. And so if this if this guy is the, okay, that's the e to the minus t over t2 star, but this guy right here, whatever you got up to, multiplied by e to the minus t over t2 star star. So that fall off is going to be a faster fall off than it would if you had just left the gradient off. So basically you damage it, and then you undamage it, and you get an echo, and then you continue to damage it. And again, the reason why we do this is because we need the gradient on to do spatial encoding, and we'll see that we'll try to put the whole picture together with the Fourier transform on why we actually want to mess up the phase of the signal. In fact, that's critical to how we code for space. Okay, so that was so everybody okay on just basic gradient echo. So sort of makes sense. So you can do a whole bunch of these, just like with spin echo, and it's worthwhile just sort of writing it out so we can see how this works. So if we just do one RF pulse, so just one RF pulse, we could do a series of gradient echoes, and this is very commonly done. So here the idea is we turn the gradient on, sort of negative like that for a while, and then we go positive, and then we go, an equivalent amount positive, and then reverse again, and then do something like that. So if we do that with the gradient, what would we expect? We would expect to get up to that envelope, the T2 star envelope, multiple times. And so the idea is that if this is our starting point from whatever we did, our alpha pulse, then, and this is the fall off, so that's the e to the minus t over t2 star fall off, the normal FID fall off. Then what's going to happen with our signal is that right here we'll get everybody back into phase, and so there'll be a big signal like this, and then it will come back, something like that. So that'll be our first echo. And then we'll continue to damage it, and then it will come back over here like that for like a second echo, but that's going down by e to the minus t over t2 star, and then there'll be a third one over here like that, and there'll be a fourth one over here. So you can do a whole bunch of these like that. Each one gets smaller as we go down, but we can have an echo train, a gradient echo train. So this is, gradient echo train. And it's very similar to the spin echo train. And what is the kind of equivalent thing that we would have done with a spin echo? At this point, we would have done a 180. So if we did a 180 over here like that, we didn't do one here. So this would be the spin echo equivalent. So when we reverse the gradient, that's when we would have done a spin echo. Now it's different than a spin echo because the spin echo is like a hammer. And so you just blast the spins, inject energy, and flip them over. And then they do their thing. They just recover that, whoever was ahead is behind, and then they slowly catch up. The gradient echo is different. You got to keep the gradient on. So like in this case, you just blast it, and then the rephasing just occurs, without any further intervention. In this case, we've got to keep the gradient on that whole time in order to have the equivalent effect of an RF pulse. And so what would happen is, like, if at this point you did another 180, you would get another spin echo at the same place. So there is no 180 in this sequence here, but it's just to sort of make the analogy of where the 180s would be if you had a spin echo, to make a spin echo here instead of a gradient echo. Okay, so people okay on the gradient echo. This is like one of the most common pulse sequences that we use. So if you look at what the scanner is heavily used for, functional MRI is a sequence that's a gradient echo sequence. And why is it a gradient echo sequence? Because we're actually looking for a static field offset. So we're actually specifically trying to measure a static field offset that's caused by the deoxyhemoglobin. That's what causes the offset. And so we're actually we want the T2 star signal. We don't want the T2 signal because that one doesn't have a big bold signal from the oxygenation difference. So we're actually looking for something that's a T2 star thing. So that's why we do a gradient echo when we're trying to do a functional MRI. But if you actually look at, it's important to sort of get the scale of these things. So if this was an RF pulse, and here's our standard, FID. So here's our FID. Let me make it a little bigger. So that takes, this is pretty short period of time. This takes like only about 1/10 of a second for this to fall off. So this is the normal FID like that that's falling off if we didn't do anything. So what do you do for EPI? So what is EPI? So with EPI, it's called echoplanar. We'll talk about this more, but echoplanar imaging. So, this is like 100 milliseconds, so not very much, 1/10 of a second. So last time we were talking about spin echo, and a couple hundred milliseconds later, we could do a pulse and get an echo. We could get an echo to appear. So this is 100 milliseconds for this single FID. And what do you do with echoplanar imaging? You just like slam the gradients on. So slam this guy down to the floor and then slam it back up again and slam it back up. So you do all these echoes just in the less than 1/10 of a second that it takes for the FID to decay. So that's the same thing as this. You're doing that, except just doing it all within the FID. So that's, and whereas if you're doing a spin echo, you could do a 180 pulse, over here, and then what would happen is like that amount of time later, you would get a spin echo that you could record. So this would be your spin echo back here. So echoplanar imaging is very different. You're just like blasting the gradients on and off, doing this like super quickly so that you could actually, get all your data out. You could get a whole bunch of points, because the problem is, you've got to record tens of thousands, hundreds of thousands of data points. So we'll go over that in more detail how this works. But this is if you want to like very quickly record 5,000, 10,000 points in order to get a whole slice worth of data. That's what you would do. You would do this gradient echo very quickly. Okay. So all happy about gradient echo? So it's sort of a not very morally upstanding echo, but and it's used a lot. So you don't get anything, you don't recover anything that you wouldn't have gotten if you just had done nothing. So that's the gradient echo. Okay, all good. Makes sense. It's pretty straightforward. Okay, so now what we're going to do is start talking about the homework. So how do you do the problems in the homework? So these problems are basically just applying those solutions to the Bloch equation recursively. So the idea is you calculate the value of the magnetization at some point, and then another pulse happens. And so then what we have to do is take whatever the magnetization was that we had just calculated and insert it into another copy of the Bloch equation. So that's fundamentally how you solve those homework problems. So what's the absolutely simplest thing we could do? Simpler than spin echo, simpler than gradient echo. What's the simplest thing we could do? And that's saturation recovery. And so what does that mean? So what does saturation mean? So saturation means we sort of did something that essentially blew away all the longitudinal magnetization. That's kind of the meaning of saturation. So, and how do you do that? We do that by basically just doing a 90 degree flip. So if we start off with, this amount of longitudinal magnetization, in the z direction, and we do a 90 degree flip, a 90 degree flip will turn all of that longitudinal magnetization into transverse magnetization. So, and then remember the longitudinal magnetization is invisible, can't record that. And so the only signal that comes out of the brain is the transverse part. And so what we're going to graph here is the longitudinal part. This is the invisible part. So the part that you actually can't record. And so what is our saturation recovery pulse sequence? It's the absolute simplest thing you can do, which is just do a sequence of RF pulses that are spaced exactly the same distance apart. So just that distance, and then just repeat, and then that distance again, just repeat. And what we want to do now is try to figure out when do we get to a steady state where the same thing is happening for every additional pulse after that. So that's what we're going to try to figure out. And so what will happen? What will happen in our signal here? Well, if we go down all the way to our signal, so way down at the bottom here, we're going to so what I'm plotting over here is the invisible longitudinal magnetization. And so this is the RF, stim. So that's what we're, RF, transmit, injecting RF power into the sample. Here what we're plotting is how much longitudinal magnetization do we have, the invisible part. But separately, there's the amount of transverse magnetization, which we don't care about in this particular diagram, but just to make sure that we sort of know, what corresponds to what. So here's the transverse magnetization. That that one is going to have a signal in it. This, FID like that. So a signal that dies away in about 1/10 of a second. Okay, but we're not paying attention to that. All we're paying attention to it is how much longitudinal magnetization do we have. And so what do we start off with? So what we start off with, here's a long time. So why are we doing a long time? That's so that we can make sure that we've gotten all the way up to our equilibrium magnetization. And so what is that equilibrium magnetization? It's, mz0. And what is that? That's basically, we know from the very earliest equations, that's basically the proton density, because the mz0 strictly depends on how many protons you have and whatever the Tesla is. So for a given Tesla, the only thing that controls that is the number of protons, just how many protons you have. And so it doesn't matter if it's white matter, gray matter, it's just, there might be a difference in number of protons in white matter and gray matter, slight difference, and then you would see it, but it doesn't matter about what the T1 and T2 is. So that's the proton density, basically. And so when we turn on the RF pulse, say we turn it on just exactly right so that we get a 90-degree flip. So however much RF we need, so we get a 90-degree flip. And that's going to give us a nice big signal. That would be the biggest transverse signal. So we basically turned that longitudinal all the way into transverse. And then what happens? So then what happens is, here's where we would get back to if we just didn't do anything for about, 5 seconds. But say the amount of time between these is, say, like, 1 second. So what is this time? This time is called the TR. That's the definition of TR. And it just means, time to repeat. So what's the time that you repeated your RF? And so each one of these is exactly the same. So this is the definition of TR, the time to repeat the RF pulse. And let's say, for example, so 1 second. So if that's 1 second, that's not long enough to completely recover, because it takes T1 time to recover. And if T1 is something like, 2 seconds or 3 seconds, then we're going to have to wait like 4 or 5 seconds till we get pretty close to mz0. And so it won't have recovered all the way. So we'll just sort of go up like this. And if we had waited like, 6 seconds, we'd get all the way back up there. So now what happens? So now we do another RF pulse and slam it back down, turn slightly less. And so what's going to happen? Well, if we look over here, there's going to be a slightly smaller signal coming out. I exaggerate out what the difference is, but it's going to be slightly smaller because we started off with less longitudinal magnetization. And then what will happen? Exactly the same thing. So we'll just go, this curve will be exactly the same as it was the last time. And so it turns out, by the time we get to this point, we're in the steady state where nothing changes. So the steady state from there, it'll be exactly the same from there on. So can we write down just the equation, the simple Bloch equation for what our signal amplitude should be? So this is our signal. So this is our, sig amplitude. So that's what we actually can record. We can't record the we can't record this longitudinal magnetization because it's changing so slow that it doesn't make any RF signal. Okay, so what's the equation for this? So the equation for this is just that solution to the T1 regrowth that we did way back when with the Bloch equation. And so that equation is the MZ0, sorry, not MZ0, the Z magnetization right before the RF pulse. So the Z magnetization right before the RF pulse is equal to, let's run the Bloch equation starting at this point. So if you run the Bloch equation starting at time t equals 0, what does that look like? Well, it looks like the solution to the Bloch equation with TR inserted in as the time. So it would be MZ0, that actually is the MZ0, so that's this proton density. And then the first term in the, remember there was two terms in the solution to the differential equation part of the T1 part of the differential equation. There was one term that was time dependent, and then there was another term that was the initial condition. And so here it's, normally the Bloch equation would have, this Bloch equation solution would have had T over T1, whatever the current time is, divided by T1. But now what we want to do is just insert T1, insert TR in there. So this is just a single time point solution to that Bloch equation curve, because we just want to know, like, what is it right here? So this is, 0 minus just before, and then, this right here is 0 plus just after. So we've inserted in TR for the time point there, but then there's another term, and the other term is plus whatever the starting magnetization was. So that's MZ, not MZ0, MZ at, right after. So this guy is, n minus 1 pulse, whereas this guy is the n pulse. So basically what we want to know is, like, what was the magnetization that we started with back here? That's what this thing is. So let's put that, put an arrow. So this guy is, whatever magnetization we started with right after the pulse. So what's that? Well, if we did a perfect 90, the Z magnetization, the longitudinal magnetization, that's the Z magnetization, is 0. So this equals 0. So we can just say, okay, you can get rid of that guy. I didn't write out the rest of the equation. There's an e to the minus, there's a minus there, sorry about that, minus TR over T1. So if this thing is 0, then it's just going to 0 out this part. And so the whole thing will be 0, and you can get rid of this guy. So just cross this guy out. And so basically, what's our bottom line equation? Well, our bottom line equation is the Z magnetization immediately before the pulse is equal to the XY magnetization immediately after the pulse. So this amount, this thing is the signal amplitude here. So this explains how we record T1. The only way we can record T1 is do something that allows some T1 to get somewhere, like here, and then turn it into transverse magnetization by doing a 90-degree flip, and then hopefully before there's any decay from T2, record the signal really quickly. And so that's how you essentially are able to measure the T1. But you can see, of course, there's always these other decays, so that's why we say T1 weighted, because there's some proton density effect. Proton density might be different between your samples. There's some T2 difference between your samples. But if we want to focus on T1, then what we want to do is try to not have much T2 decay, so record the signal quickly, early in this FID before it has a chance to die away. So this is like what we'll see throughout the rest of the course. That's the problem with MRI. There's like 10 things affecting the signal, and you're just trying to sort of like cause most of the effect to come from something. And that's how pulse sequences work. They adjust different parameters in them so that they focus on one feature rather than another, but you can never completely remove, it's very difficult to completely remove the effect of the other features. So what is our bottom line equation here? It's a very simple equation. It just says the signal that we're going to get if we just do a sequence of RF pulses is just equal to 1 minus e to the minus TR time, whatever that is, over whatever the T1 value is. And so that's the bottom line. So that's a simple one. Now, all we have to do is imagine if you had a more complex pulse sequence where you did some other pulse that wasn't evenly spaced, just stuck another pulse in there. Then what are you going to have to do? You're going to have to sort of calculate wherever you stuck that pulse in, take whatever the longitudinal magnetization was, and insert it back into another copy of this Bloch equation. So that's fundamentally how you work these problems. So you do some calculation for a particular time point, get an answer, and then take that answer and stick it into another copy of the Bloch equation that's going to have some further relaxation or decay. So basically this is recordable. That's what we can record. And this one, is the amount of magnetization longitudinal recovery. And that's invisible. And this is recordable magnetization transverse. Okay, so this is the very first pulse sequence, just a sequence of evenly spaced RF pulses, all the same size. Okay, so everybody okay with this? Questions about this? So if you know anything about, if you've ever done, has anybody out there ever done any fMRI experiments? Nobody out there? Yeah, if you've ever done an fMRI experiment, you know that this is not true. So why is this not true? So if you've ever done an fMRI experiment, what you do is you collect an image of the brain every second or two, a low resolution image of the brain every second or two. But if you know anything about fMRI, what happens is you typically throw away the first 8 or 10 images of the brain. And why do you throw them away? You throw them away because they're too bright. And so clearly my whole thing here is not true. Like, how come we said that you reach a steady state after one pulse, and so everything should be exactly the same But that's clearly not true, because you typically are going to throw away 10 images because they were too bright, because they were not the same brightness. So this is recordable MT, which gets turned into image brightness, or voxel brightness. So this thing right here is actually, you can think of that as how bright the voxel is. So why, what explains that? How come it's not true? And so for this, we have to draw a bigger picture. So here's a big version of this. So this is a big version of that. So what's actually happening? Well, so say this is MZ0. So that's our equilibrium magnetization. And so we've waited a long time, a couple seconds, and so we've got, we get all the way up to equilibrium magnetization. And then let's get this it's about here. Make sure I got my. So now we do an RF pulse. But say we missed, and we didn't get exactly 90 degrees. Say we got like that. Now, why would we do that? Well, it turns out if you do an RF pulse at 3 Tesla, the amount of flip that you get in different parts of the head is going to be off by like 25%, plus or minus. And why is that? Well, it's because the RF doesn't penetrate completely uniformly into the head. And so there's going to be substantial difference in the amount of flipping in different parts of the brain. And you could easily be off by this much. So now let's going to see what happens. So in this very simple case, we could throw out this, this initial condition, because we said it was just 0 because we went to 90. But now let's sort of look at what happens. So now what happens is we're going to have this amount of transverse magnetization left. And so let's label the time points. So here's time point 1. Time point. And then we did our flip and we kind of missed, and that was time point 2. And so now we're going to consider, we've got this much, transverse left. So this is, initial, longitudinal. I spoke wrong, longitudinal. So we got that much longitudinal left. And what's going to happen, that's going to, grow back up to some point, say like about here. And so that will be, time point 3. And then we're going to flip that one again. So flip that guy again. And so it's going to end up, over here. So that will be time point 4. And that's going to give us less magnetization. So if we go over here, we're going to get less magnetization. And so when that one regrows, exactly the same amount of time, it's going to, regrow up to, about that distance. About that distance. Not exactly, but pretty close. And so then that will be our time point 5. And then when we flip it again, we'll sort of end up over here. And now notice that now the amount of difference is smaller, You can see it's a smaller difference here. So that's a good thing. And so when we flip up the next time, we'll be closer to where we were last time. So here we'll be closer to where we were last time. So this will be, that was 0.5, and then we went to 0.6 over here, and then we went to 0.7 over here, and this is the 0.7. There's 0.7, and then when we flip that one, what will happen is each time we'll get closer and closer, so there'll be a less of a decrement here until we eventually sort of home in on after about like 10 seconds, we'll home in on our, steady state. So we'll eventually get to the steady state here. Now, this was just kind of a graphical picture of it. If you wanted to actually do this correctly, you would have to sort of like, calculate using this with a non-zero for this part, for this initial condition. This guy's initial condition. So you'd have to stick the actual initial condition in. Here's these initial conditions right here. They're different each time. So you would stick in the real initial condition, calculate what the MZ0 was, and then get a new initial condition, stick that one back into here, calculate a new MZ0, and just do that over and over again. And then if you did that, you could see that you'll eventually get to a steady state. But it will take 10 seconds to get there. So this isn't that big of a difference, So, why do you even bother with that in fMRI? And the sad reality of fMRI is that, fMRI, is a ridiculously low signal to noise measure. So you get nice, colorful pictures if you look at any MRI result on CNN, but unfortunately, the signal that we're looking at is pretty tiny. So what do we have to deal with? Well, we have to deal with things like, a 1% change in due to heartbeat. So every time your heart beats, what does it do? Well, the whole point of it is to shovel some more oxygenated blood so your brain doesn't die. So if we're trying to measure oxygenation, well, it's obviously going to mess up our signal because there's like a 1% pulse every time the heart beats. What about breathing? Well, yeah, breathing is another one. So it's important to breathe and to get oxygen into your blood. Every time you breathe, that's going to change the oxygenation level. So you can see another signal that has to do with the breathing signal because it's flipping the oxygen level. What if you moved? You could get like a 3% signal if you moved. And what does that come from? Well, like you have one voxel and you move one voxel into another voxel, and maybe that voxel has, a different brightness. That's going to cause a horrible, nasty thing. What kind of signal are we looking for? Well, a lot of times we're subtracting something like, faces versus upside down faces. We could be looking for 0.1% signal. A lot of cognitive experiments, cognitive subtraction. You're looking for something under 1%, well under 1%. And so, what is this difference here? This difference is like, 5%. So that's why, you have to really make sure that we're in the steady state so that we don't get this giant artifactual brightening at the beginning of our experiment, which might have had, say, the upside down faces. And if they were the upside down faces, then you would get sort of a 5% extra signal for the upside down faces, and that would mess up your analysis. So yeah, so we'll be fighting with this a lot, like, it's a very low, unfortunately, it's a very low signal-to-noise method. Okay, so any questions about this? So gradient echo, sort of the inferior cousin to spin echo. You mess it up and then fix it, but we do that because we almost always have to have the gradient on. And then saturation recovery, how do we apply, this is the solution to the T1 part of the Bloch equation. Yeah, that's what this thing is. This is, solution to T1 part of Bloch. And how do we apply it? We apply it just by inserting in some actual times in our pulse sequence into the equation, calculating something, and then sometimes for like later problems in the problem set, taking whatever you got and inserting that thing in as the initial condition and then calculating again. Okay, all good? You guys fiddling with the problems? So next time we'll talk about problem 2. I'll put the equation up for problem 2 and we'll sort of try to get an idea of how to sort of derive that that equation for the spin echo. Yeah. Oh, spin echo versus gradient echo? Well, sometimes gradient echo, we use gradient echo because for functional MRI because we want to calculate blood oxygenation, but we might want to actually not care about blood oxygenation and want to actually measure the T2 value of the tissue. So if you want to actually sort of emphasize that, and a lot of scans looking for tumors, for instance, are going to look for, they want a T2 weighted scan that will, because there's a large difference between a tumor tissue and non-tumor tissue in T2. And so in that case, you don't want a T2 star scan, you want like a T2 scan. In general, a T2 type pulse sequence is going to be less subject to distortions. That's another reason why you might want to do a T2 scan if you want like an undistorted picture of the brain, because T2 star scans can have distortion in them. In the case of functional MRI, we just have to put up with it because we're trying to actually record something that affects T2 star, and so we just have to use a T2 star scan even though it's more distorted. But that's the reason why we might want to just see if something has a difference in T2 and we don't care about these static offsets. Okay, so next time, spin echo. So spin echo relevant to problem 2.